13.4 Partial Derivatives Part 2. For a warm-up, turn off the video and turn it back on after you take these two partial derivatives, f partial x and f partial y. Check your work. Notice that f partial x and f partial y each give a new function. This is what I'd like you to do with the new functions. I'd like you to find their partials with respect to x. Turn the video back on when you're done with that, please. Check your work for f partial x, partial x. And check your work for f partial y, partial x. Instead of our second partial being with respect to x, we could have our second partial be with respect to y. Please find those. And check your work. The function f has two first partials and four second partials. And f partial x partial y is equal to f partial y partial x. Does this always happen? And how can we know whether or not it will happen? As long as they are continuous, f partial x partial y is equal to f partial y partial x. Rather than saying f partial y partial x, we usually just say fyx. Let's do a function of three variables. Again, turn off the video and find these three partials. And you can check your work. I am about to get a bit technical here. It is tempting to say that f is differentiable if the partials exist. While that is certainly necessary, it is not sufficient for differentiability. In single variable calculus, a function is not differentiable at a jump, a cusp, or a corner because there is not a unique tangent line. For it to be differentiable, it needs to be smooth. This is also true for a function of two variables. For the function f to be differentiable at a point, it must be smooth at the point with something analogous to a unique tangent line. Let's go back to single variable. The function f is differentiable at a provided this limit exists at a. For the limit to exist, the function needs to be smooth at a without any jump, cusp, or corner. We define a function epsilon in this manner. Then change of y can be written in this new manner, and f is differentiable at a provided epsilon goes to 0 as change of x goes to 0. There are similar requirements for a function in two variables, but as you can see, we now have epsilon 1 and epsilon 2. So it has become more complex. Does this mean we have to find epsilon 1 and epsilon 2 each time to find out whether or not a function is differentiable at a point? Well, here's the good news. As long as the partials are continuous, f is differentiable. A side note, if a function is differentiable, then it is continuous. And by now, you probably know that if it's continuous, it might be differentiable or it might not. However, if you do know it's differentiable, then you do know it's continuous. Is this function differentiable at 0, 0? The function is not differentiable at 0, 0. We know this because we have already discovered in the previous section that the function is not continuous at 0, 0. Since it's not continuous at 0, 0, it can't be differentiable at 0, 0.